All right, guys, we are in for quite a treat today, and no sarcasm even intended. So we're going to talk about inverse of a matrix. You thought determinant was getting a little bit crazy. Just wait for what we're doing today with inverse of a matrix. So let's first of all review how to find the determinant, because that will have some bearing on what we do today with inverse calculation. So remember last time we talked about finding the determinant of a 2 by 2 matrix. We take the product of the diagonals. So here 2 times 8 minus 4 times 4. So here I have 16 minus 16. So in this case, it is 0. Our determinant was 0. We haven't talked about the implications of that, but ideally it's a non-zero outcome. If it is 0, that has some interpretations, but we'll reserve that for later. For a 3 by 3, finding the determinant, remember we said we're artificially extending the matrix by stealing the first 2 columns and just copying them over to the side. So 1, negative 4, 7, 2, negative 5, 8. And then we are going to be again taking diagonal products, I should say. Let's erase these. And so first of all, we're going to start with the leftmost. 1 times negative 5 times 9. That's going to be negative 45. Plus 2 times negative 6 times 7, which is negative 84. Plus 3 times negative 4 times 8, negative 96. And then all that minus products in the other direction. 7 times negative 5 times 3, negative 105, plus 8 times negative 6 times 1, which is negative 48, plus 9 times negative 4 times 2, which is negative 72. These poor neglected numbers. Do you see some of them aren't even used? Look at these guys just hanging out, spectating the whole process. Okay, so if we go and combine them, negative 45 minus 84 minus 96 gives me negative 225 from the first group, minus negative 105, minus 48, minus 72, negative 225. And then look at this. We have this negative, which is plus. So together this makes 0. It's all that work for nothing, just a 0. Anyway, we'll be revisiting what that means as far as inverses go if our determinant is 0. But that's the process in a nutshell. Okay, so we're going to talk about, let's just first of all introduce that the inverse matrix, or the inverse of a matrix, I'm going to change this color because I'm going to tear that one. A 2 by 2 specifically, it's similar to the reciprocal of a number. So when you multiply a number and its reciprocal together, you get 1, right? So if I take 2/5 times 5 over 2, this would give me 10 over 10, which is 1. So that's the idea of multiplying a number with its reciprocal. Similarly, when you multiply a matrix A by its inverse, and it's denoted as just matrix A with a little negative 1, almost looks like it's a power, but it's a superscript, not an exponent. You get the inverse matrix. Not the inverse, the identity matrix. And because in our previous lesson, remember, we likened the identity matrix to, it's kind of like the matrix equivalent of a 1, where we have 1s everywhere in just the diagonal, but 0s everywhere else. So when I multiply a matrix by its inverse, we get the identity matrix. So it's kind of like multiplying a number by its reciprocal to get 1. So in order to find the inverse, calculate it by hand, when it's a 2 by 2, we're going to follow these steps. We first of all switch the positions of A and D in the matrix. So we kind of update the matrix to look like this. D, C, B, A. So notice that I've switched, or I've interchanged the A and the D. And then we change the signs of B and C. So this second change is going to have the effect of making my matrix D, negative C, negative B, and A. Okay, so we're making some changes to our original matrix. And then we multiply this new matrix by 1 over the determinant of the original matrix. So lots of changes here. But if we were to summarize how to write this all out, we say that the inverse of matrix A, this is shorthand for inverse of matrix A, is equal to 1 over the determinant of A, okay, times this new matrix where we've switched some things around, D, negative C, negative B, A. So we kind of make some updates to matrix A, and then we multiply it by 1 over the determinant of that matrix. And that's going to give us our inverse matrix. So let's put this into play. Oh, and I should say that the last line, a matrix will have no inverse if the determinant of that matrix is 0. So if the determinant is 0, then we won't be able to find its inverse. Just a little note to make there. Okay, so first problem, let's go ahead and find the inverse of this matrix A, where we have entries of 3, 9, 4, and negative 6. So first of all, if we want to find, we're referencing, let's kind of erase this here. We're going to erase this and emphasize that this is the piece, this is the formula that we're using in our next calculation. Okay, so I'm going to jump back down here and say that the inverse of matrix A equals 1 over the determinant of A times this kind of switched around matrix of D, negative C, negative B, and A. Okay, so first of all, the determinant of my matrix up at the top here would be 3 times negative 6 minus 9 times 4. And whatever that evaluates to, I'm multiplying by the matrix where I'm switching, or I'm interchanging my A and my D. So negative 6 up in this corner, 3 in this corner, and then I flip the signs of my other two values, C and B. So this becomes negative 9, negative 4. This whole determinant here would just simplify to negative 18 minus 36, which should be negative 54. All right, so really what I'm just taking here is negative 54, well, all under the bottom of the fraction, right? Because this is 1 over the determinant. So 1 over 54, let's bring this down here. 1 over 54, okay, times the matrix negative 6, negative 9, negative 4, and 3. Okay, and remember, with as far as how this works, I just simply multiply the fraction to each piece. So I would have negative 6 over 54, negative 9 over 54, negative 4 over 54, and 3 over 54. And we want to reduce these fractions where we can. So if I go in and reduce my fractions, (6 over 54 reduces to negative 1/9. 9 over 54 reduces to negative 1/6. 54 and 4, let's see, that's not going to reduce all the way, but they are both divisible by 2. So I can go ahead and change this to negative 2 over 27. And then 54 is divisible by 3, so this would reduce to 1/18. So these are kind of heavy lifters, huh? I'm going to find the inverse. Remember that you can check your work if you're using a graphing calculator. So I would definitely recommend, again, you don't want to be relying on this as a crutch, but it is a good idea to just check your work. So if I'm entering 3, 4, 9, and -6, and I want to find the inverse, if I go to my matrix, there is an option to determine, let's see. Oh yeah, no, inverse actually is listed. So if I pull my matrix and I want to find the inverse, we'll actually, let's save this for later in our video. Let's now go ahead and confirm the second part here, that when I multiply my matrix A by the inverse, which I just calculated, I'm going to, in fact, get the identity matrix. So I'm going to jump down over here and just copy down matrix A, which is 3, 9, 4, -6. And let's multiply these two together. So 3, 9, 4, -6. And I want to multiply these two matrices to see if I do, in fact, get the inverse. So I'm taking 3 times -1/9 plus 4 times -1/6 for my first entry. Okay. Over here, I'm taking 3 times -2/27 plus 4 times 1/18. Down below, 9 times -1/9 minus 6 times -1/6. And then over here, 9 times -2/27. Woo. Minus 6 times 1/18. Okay. So we're looking to confirm that we get the identity matrix. So if I take 3 times -1/9, and to that I add 4 times -1/6. Why do I have a -1? What did I miss there? Something. Did I? Sometimes you end up missing pieces here. 3, 9, 4, -6. This is, I'm telling you guys, be on the lookout for this. Definitely can happen as you're working through these. It's like kind of like working with the systems of equations where you have one tiny thing that throws off your entire process. So somewhere along the lines here, that's very curious. -18. You know what it was? I think we dropped out. Look at that. That's all it takes. Back here, 3 times -6. Why is this not writing? 3 times -6 minus 9 times 4 should give me -54. So this guy was negative, meaning when I multiply it in, positive, 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 negative. So if I drop those all down, oh yeah, because I just reduced this here. So positive, 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 negative. So when I go to multiply them together, this should have been, there we go, positive, 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 positive. Or just flip all the signs. And this is just a good way to illustrate how you can redeem yourself. Even if you go through all of that work, you don't have to start from scratch. Sometimes it's just one tiny thing to kind of backtrack. So here we have it. If I go ahead and simplify 3 times 1/9 plus 4 times 1/6, that does give me 1. And then this entry here, 9 times 1/9 minus 6 times 1/6, that gives me 0. Over here, 3 times 2/27, 2/27 plus 4 times negative 1 over 18 is 0. 0. And then down below, 9 times 2 over 27. 2 over 27. Minus 6 times negative 1 over 18 gives us 1. There we go. Oh my goodness, keep writing with the highlighter. So again, guys, you really want to be patient with yourself when you're working these out. I distinctly remember doing this as a student and just like pulling my hair out. Don't pull your hair out. Just be patient and know that sometimes it's literally like that was that one mistake that I made that threw the whole thing off. So you don't have to throw out, the baby with the bathwater if something doesn't go right. Just go back up to the top, glance through your work and see if you can observe where you went wrong. And this really speaks to the point too of show your steps. Like if you take shortcuts and just do a bunch of stuff in your head, you can't go back and see where you went wrong. And then it's impossible to review, where you got lost. So yeah, okay, that's enough of that. So number 2, we want to make up a 2x2 matrix that does not have an inverse. This gets back to the point that, like we said here, a matrix has no inverse if its determinant is 0. So if I just essentially come up with a matrix that would have a determinant of 0, and we know that our determinant for a 2x2 is taking the cross product, so maybe I just pick some numbers, 8 and 2, and I know those will multiply to make 16, minus some other 2 numbers that would multiply to make 16. So if I came up with 4 and 4, right, that together is going to give me 16 minus 16, which is 0. So if the determinant is 0, it does not have an inverse. So this matrix here would not have an inverse. Okay, so now let's go ahead and practice this a little bit more. We're going to find the inverse of these 2x2 matrices. Remember, you're using this very advanced, or not advanced, but involved algorithm where we say that the inverse of the matrix A, if we're calling this A, equals 1 over the determinant of this matrix times the kind of special matrix where we're switching things around, D, negative C, negative B, and A. Okay, so if I go and take my determinant here, I have 1 over my products. So 1 times 3 is 3, minus 4 times 0 is 0. And then my special matrix, if I do this little switch around, I have a 3 here, negative 4, 1, and 0, right? Because I'm just interchanging these guys and then negating or changing the signs on the other 2 numbers. So if I simplify, I have 1/3 times this whole matrix, 3, negative 4, 0, and 1. And taking that a step further, if I distribute in a sense that 1/3 in, I have 1/3 times 3, which is 1. 1/3 times 0 is 0. 1/3 times 4 is negative 4/3. And 1/3 times 1 is 1/3. So that would be the inverse of this matrix. And remember, that's to say that this matrix here, if I multiplied it by my starting matrix, or other way around, if I take the product of the 2, then I would expect to get the identity matrix. Okay, and let's look at this guy too. So same thing. We know that we're going to call this guy B. The inverse of matrix B is 1 over the determinant of B times the special matrix where I'm switching these guys around. So I have D, negative C, negative B, and A. And if I jump into my calculation, I have 1 over 4 times 4, which is 16, minus 2 times 8, which is 16. That happened to be the matrix that we looked at before that would not have or that its determinant would be 0, so we wouldn't have an inverse. But let's just continue with it. So we switch these guys around, 4 and 4, make this negative 2, negative 8. But notice already I'm going to run into an issue here when I take 16 minus 16 to get 0. And this is an undefined fraction. I can't take a number and divide by 0. So because this is undefined, there's going to be no inverse. So there's a failure to even perform the calculation. So there would be no inverse for this matrix. We could have also just found that more readily at the beginning by seeing that, oh, there's no determinant, or the determinant is 0 specifically, so I won't be able to find the inverse. Okay, number 5, let's call this matrix C, and we know we're finding the inverse of C. Our formula is 1 over the determinant of C times the switch around matrix. There should be a name for this. Anyway, D, negative C, negative B, and A. Determinant here, I'm taking 1 over 6 times negative 2, which is negative 12, minus 14 times negative 1, which is going to become plus 14. And then interchanging my values, I have negative 2 here, negative 14, positive 1, 6. This simplifies to 1/2 times negative 2, negative 14, 1, and 6. And so if I distribute this guy in, I have negative 1, negative 7, 1/2, and 3. So that would be my inverse. And again, that's to say that if I multiply the matrix with its inverse, I would get the identity matrix. Okay, you'll be happy to hear that you won't always have to find these by hand, nor will you be expected to calculate the inverse of a 3 by 3 matrix. So we're going to go ahead and use a calculator. Okay, so we want to find the inverse of the following matrices using a calculator, and we want to write the determinant of each matrix as well. Okay, so looking at these matrices here, we want to first, let's see, where is, you know what, guys, I think I am, let's name it first. So if I go ahead and edit my matrix name, so I'm going to go ahead and call this guy here A, and I'm entering 4, 5, 8, 2, 5, 6, 9, 4, 14, and 18, typing this into my calculator. And I want to find the determinant of this matrix using my calculator. Okay, so if I go ahead and name this one A, and I want to find the inverse of this matrix, and I can use my math tab in my matrix kind of repository for functions on my calculator to go ahead and pull this one here. Okay, I'm just kind of giving you guys some time delaying as you are probably typing things in here, so we don't go too quickly. Another alternative too, if you are at home and you do not have a graphing calculator, there are alternative ways to look this up as well. Okay. So if, for example, if I were to just even Google inverse matrix calculator, you know, don't hesitate to get creative when you're at home trying to find ways to do this if you don't have a calculator like we have at school. So if I want to go ahead and try this out and see what the inverse of my first 3 by 3 matrix is, then I should have -3/11 in the first column. So let's call this A. So the inverse of A will be -3/11, -9/11, 17 over 22, and then over here -1, 0, 1/2, 5/11, 4/11, negative 5/11. Okay, and if I want to confirm that the product of these two is my identity matrix, that means that I take this matrix here, multiply it by my other matrix, and I should confirm that I get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and I kind of delayed a little bit, quite a bit before, so I'll speed that one up. But if you want to go ahead and just confirm that you do in fact get the identity matrix when you multiply those two together. And remember, you can do that by naming the two matrices and then going back into the matrix function, selecting the math tab, and or actually you would pull the names tab, pull out those matrices and multiply them together to confirm that that's your outcome. Okay, so let's try another one. So now we want to find the inverse of this 2 by 2, 2, 7, 9, and 6. And again, we want to go ahead and try using a calculator. So if I go and enter 2, 7, 9, and 6, whether you're using a graphing calculator or a kind of an app online or just even a website, we should find that our inverse 2 for this 2 by 2 matrix is negative 2 over 17, 3 over 17, 7 over 51, and negative 2 over 51. Multiplying these two together, right, because we're looking to confirm that we do in fact get our identity matrix, you should find that we get 0, 1, 0, 1, 1, 0, 0, 1. Okay, and then finally this last one here, if I want to go ahead and try another calculation for a 3 by 3, this is going to be negative 1, 0, 9, 9, 1, 0, and 0, negative 9, 1. Okay, and our inverse is going to be pretty messy on this one. This guy here will have an inverse if I call this one C. The inverse of C is negative 1 over 730, 9 over 730, 81 over 730, goodness sakes, 81 over, are you just happy that we didn't have to do this one by hand? 81 over 730, 1 over 730, 9 over 730, and that is just coming from the wicked determinant that this one has. 9 over 730, negative 81 over 730, and 1 over 730. So that's just the inverse itself. And then again, you want to go ahead and name these two matrices in your calculator, multiply them together to confirm that you get the identity matrix. And our identity matrix here would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and that's it for today. Again, kind of a long process, guys, but that's why we want to see how it does work by hand, but that you do actually have the functionality in your technology to automate this process.